Alright, so this is section 4.4 continued. I want to do another example of an optimization problem. So here we're trying to find the maximum volume of a cone. We're told that a cone is constructed by cutting a sector from a circular sheet of metal with radius 20. The cut sheet is then folded up and welded. So then we want to find the radius and height of the cone with maximum volume that can be formed in this way. So we're not told how big the sector is that's cut from this circular sheet. We just know that someone cuts out this chunk and it goes away. Okay, it's not part of the problem. That is the piece that's cut out. And then what happens is that these two edges on either side of that missing sector are welded together to form this cone right here. And we can assume that this cone is hollow. Okay, so from the picture it's kind of hard to tell, but this is going to be a hollow cone. Alright, so we have a picture. We want to optimize something. So let's look for some keywords about what we're supposed to optimize. And right here I see it says maximum volume. Okay, so that's my key, that we're trying to optimize volume here, and we're trying to find the maximum volume. So I want to find the maximum volume of a cone. So I'm going to start off with the volume of a cone, which is 1/3 pi r squared h. Okay, so we have the height of the cone, that's h. We have the radius of the cone, which is r. So that is our objective function. We are going to try to maximize this. What is our constraint? Well, this one is a little less clear-cut, I'd say, than the last example I worked through. So let's go off of what we know. Okay, so let's reread the problem. We know that this cone comes from a circular sheet of metal with radius 20. So that 20 could be pretty important. So I'm going to underline it. And then we're asked to find the radius and height of the cone with maximum volume. So maybe we want to figure out how to relate the radius and the height and this radius of 20 that we were given. So how can we do that? Well, if we look at the second image here, okay, so looking at this cone that has been welded out of this sheet of metal, I'm going to draw it in a different way. I'm going to draw it like so. Okay, so here's our cone. If I drop a perpendicular down and draw a horizontal line over, I know that I have a right triangle whose hypotenuse is 20. Okay, so I know the hypotenuse is 20 because this edge here, okay, we're given that that's equal to 20, and that has been welded together somewhere along this cone. Okay, so that means that this side here, this hypotenuse of the right triangle, has to be 20, and then we're calling the height of the cone h and the radius r. So now I have a way to relate r, h, and 20. So I have a way to relate the radius and the height and a number. So that's going to give us our constraint function. So the question is, how do I relate these? Well, you know, that just takes some, I'd say, some practice and some thinking about it, and maybe even some trial and error. But I can tell you, I don't think we want to introduce any kind of trigonometric function, because that's going to introduce another variable with a theta, or whatever we might call an angle. So maybe instead we could think about the Pythagorean theorem. The Pythagorean theorem would tell us that r squared plus h squared is equal to 20 squared. So now we have a way to relate r and h and a number. So I'm going to solve the constraint for one of the variables. I'm going to solve it for r. So I know that r squared is equal to 20 squared minus h squared, Well, 20 squared is 400, so we have 400 minus h squared. R is a radius, so it's going to be positive. So when I solve for r, I square root both sides. I have r equals square root of 400 minus h squared. Again, r is positive, so we can just take the principal square root here. I'm going to plug that into my objective function. So plugging that into my objective function, I have v equals 1/3 pi times r squared, but I'm letting r equal root 400 minus h squared. Okay, so that's r squared times h. And so if I square out that square root, I get 1/3 pi times 400 minus h squared times h. Alright, so now we have an equation for volume, all in terms of one variable. Now I can start optimizing that equation. So I'm going to take the first derivative of the volume equation with respect to h. That's my next step. So v prime of h is equal to 400 over 3 pi minus pi times h squared. Again, we want to optimize this, so I'm looking for critical points. I set this equal to 0, and I solve for h. So I've got 400 over 3 pi equals pi h squared. I can cancel the pi, and I get 400 over 3 equals h squared. So h is equal to the square root of 400 over 3, which is 20 over root 3. Alright. Well, so there we found h. We've now found h. Let's find r. So we go back to the constraint to solve for r. So we have that r squared plus 400 over 3, okay, h squared is 400 over 3, has to be equal to 20 squared, which is 400. So if I solve this for r, ultimately I end up with r equal to 20 times the square root of 2/3. And I'll let you verify that. I've skipped a few algebra steps. So we have found an r and an h that optimize the volume. I'm going to leave it up to you to check that this is really a maximum, and you're going to check that it's a maximum with either the first or second derivative test. Okay, I used the first derivative test in the video that I did previously for this section, so maybe it would be a good practice for you to try to verify that this is truly a maximum or gives a maximum volume with the second derivative test. So I'll leave the verification up to you. Alright.